Hey everybody, welcome to my final project for the URI Quantum Computing Graduate Certificate Program, class of 2024. I am Brendan Berry. Quantum computing is a rapidly developing field at the intersection of physics, technology, computer science, and engineering. It has the potential to revolutionize medicine, AI, finance, material technology, cybersecurity, and many other disciplines. Its revolutionary potential stems from quantum algorithms' unique ability to leverage quantum phenomena, such as entanglement and superposition, to exponentially reduce the computation time needed to perform certain tasks. In this lecture, I will motivate, describe, and utilize one such quantum algorithm known as Shor's factoring algorithm. Shor's algorithm is a quantum factoring algorithm that was designed by Peter Shor in 1994. Before getting into the specifics of how Shor's algorithm works, let's first talk about factorization a little bit. So in mathematics, factorization refers to the process of reducing a number into the prime numbers that multiply to form it. For instance, if we have the number 200, we can factorize this by breaking it up into its primes. So take the smallest prime number 2, divide that, we get 100. We can do this again to get 2 and 50 again by 2 gives us 2 and 25. Now we can no longer divide by 2. We can try 3, but that won't work. We can do 5, and we find that we have 2 sets of 5s. So we've now reduced 2 into its prime factors, which are 2 to the 1, 2, 3 times 5 to the 1, 2. And so we can see for a number like 200, that's fairly simple to do. But if we had a much larger number with fewer prime factors, then things become more difficult, right? So if, for instance, we had 6,499, we can try to, again, divide this by 2, but it's odd, so that won't work. We can try 3. If we try 3, what we end up finding is that 6,499 divided by 3 will give us 2,166.3, repeating. So we see 3 doesn't work. We can try 5 again, but we see that this ends in a 9, so 5 won't work, and we can continue to go down this list. And what we'll find is that we won't find a solution until we get to number 67, in which case we'll have 6,499 divided by 67, and this will give us 97. And now we can continue to try to reduce 97, but as it turns out, 97 is also a prime number. So we find that 6,499 has 2 prime factors, 67 and 97. So if we try to do this the iterative way that we did with 200, we'd say it would take us much longer to arrive at an answer. And I mean, this is for a 4-digit number. If we had a much larger semi-prime number, again, semi-prime means a number that only has 2 factors, and they're both prime, this would have taken much longer to do. Now, obviously, we're doing this by hand. Nowadays, we have computers. However, it turns out that even with modern computers, the computation time needed to solve these sorts of factorization problems scales exponentially with the number of digits. So, for instance, if we have a graph here, computation time versus the number of digits of a semi-prime number, what we'd have is that for the time needed to factor a number, we'd have some sort of exponential curve like this. And so with this exponential curve, what eventually happens is that for a large enough semi-prime integer, the computation time needed will be infeasible for even a modern supercomputer to handle. It's currently thought that for a 300-digit semi-prime integer, it would take a modern supercomputer 150,000 years to do that computation. So the factorization of sufficiently large semi-prime numbers is practically impossible for even a modern supercomputer to handle. On the other hand, something interesting is that the product of 2 large prime numbers is not computationally challenging. Explicitly put, while the computation time needed to factor the large semi-prime numbers scales exponentially, the computation time needed to compute the product of 2 large prime numbers is trivial, right? So maybe that might scale something like this. It might get a little bit longer times, but nothing like this exponential. This stark contrast makes the factorization of large semi-prime numbers an excellent lock and key encryption method, right? If you have a large semi-prime number as a lock, and its factors are the keys, and it's impossible to factor to find the factors, right, because of this exponential scaling, but it's trivial to check that the keys are in fact the correct keys for that lock because the multiplication is trivial to do. Then you have a very secure lock, and for this reason, large semi-prime numbers are utilized by many popular modern encryption methods. For example, RSA, which is widely used to encrypt communications and transactions on the internet, utilizes this factorization, right? So RSA. I won't go into the specifics of how RSA works, but it's sufficient to know that it relies on the secrecy of large semi-primes prime factors. Now, how do we know that it's impossible for modern supercomputers to factor large semi-primes quickly? Right? How do we know that we're always going to have this exponential scaling? Well, we don't, and in fact, there have been many algorithms designed which significantly speed up the factorization of semi-primes relative to this iterative approach we took. However, while they've been able to make significant improvements, they've only been able to extend this exponential curve or flatten it a little bit. They haven't been able to reduce this exponential to something that's more polynomial in nature. And that's the crux of the issue, because if you still have an exponential curve, as you increase the number of digits, eventually you reach a point where you can no longer factor that semi-prime number in a feasible amount of time. And that's great news, right? Because, as I mentioned, RSA and other encryption methods utilize this fact to encrypt data. So, I mean, if it was simple to break the factorization, then many of our modern encryption techniques would become obsolete. So privacy online would all but disappear. Personal information, financial transactions, classified information, it could all be up for grabs. Now, there is an important distinction to make. Many classical algorithms have attempted to and failed to reduce this exponential scaling. However, there is, in fact, a quantum algorithm known as Shor's factoring algorithm, which is able to reduce the scaling. And we'll talk about how this is possible next. So we'll see that Shor's algorithm is able to reduce this exponential time scaling in the prime factorization of large semi-prime numbers by utilizing the inherent parallelism that quantum superpositions and entanglement allow for. But before we get to that, let's first discuss some of the background. So to begin, let's first consider a general strategy for factoring a large semi-prime number, n. So this is our large semi-prime number. To begin, we'll select a random number, a guess, g, that is between 1 and n. Note that while finding g that is a factor of n would be ideal, because then we're done, we found one of the factors, it's sufficient to find a g value that shares a common factor q with n. So that is, it's sufficient to find g that equals tq such that n equals mq. So while g itself might not be a factor of n, they share a common factor, this q value here. This is because if g and n share a factor, and we find that common factor, then we found a factor of n. In the case where n is a semi-prime number, we simply do n divided by q, which gives us m from here, and now we're done. We found our two prime factors of n. Therefore, once we have g, once we have a guess g, we simply need to compute the greatest common factor between n and g. So, greatest common factor, or you'll also often see GCF. So we'll make a guess for g that's somewhere between 1 and n, and then what we'll want to solve for is GCF of n and g. And now, looking at this, you might say, we'll want to find a greatest common factor of n and g that's not equal to 1, right? So that's our trivial one. All these numbers, all integers, will have a common factor of 1. And if we find a greatest common factor that's not equal to 1, then we found a factor. So while finding the greatest common factor may initially seem just as difficult as finding a prime factor, thankfully this is not the case. There is, in fact, a famous method for determining the greatest common factor of two numbers that dates back to 300 BC, known as Euclid's algorithm. So Euclid's algorithm. And this is an iterative approach where to find the common factors of n and g, we follow the following algorithm. So we start with n equal to g times some integer k naught plus some remainder r1. And so we'll want to solve for k naught, integer k naught, and the remainder. Once we have this, we'll move on and we'll do g equal to r1 times k1, so some other constant, plus the new remainder. And we'll continue this approach until we reach the point where we have Rn minus 1 equals Rn Kn plus 0. And at which point we say that the greatest common factor between n and g is equal to this Rn value that we find here. Note that, again, we want Rn not equal to 1, otherwise we found two numbers that are coprime with a trivial factor of 1, in which case we have to restart and try a different g. But let's just do an example here. So let's say we had the number 91, and we make a guess of 26. So we would have here n equals 91, comma, g equals 26, and we have k naught that we need to solve for, plus r1 that we need to solve for. So 26. Now 26 will go into 91 3 times. Right, that'll be 78. So 3 times 26, this is going to give us 60 plus 18, 78. And then that means that we'll have a remainder of 13, which now continuing along this formula. So we now have G, 26, equal to R1, 13, K1, plus R2, from this up here. And we again try to solve for K1 and R2. So K1 13 times 2 actually equals 26, so R2 will be 0. So we'll have 26 equals 13 times 2 plus R2, or plus 0, sorry. In which case, using what we used up here, we see that we have now solved for the greatest common factor of 91 and 26 and found that it is 13. So as it turns out, we see that we found a factor of 91, which is itself a semi-prime number. So we can solve for the other factor by doing 91 divided by 13, which will give us 7. So we found that we found the prime factors of 91 are 13 and 7. So you can see Euclid's algorithm works, and it finds us the prime factors of 91 using the greatest common factor between two numbers. However, in this case, we just got lucky and we guessed 26, which happened to share a prime factor, or happened to share a common factor with 91. If we had instead picked, say, the number 2, right, then we'd have 91 equals 2k0 plus r1, which would be equal to 91 equals 2 times 45 plus 1, which would be, because 2 times 45 is 90, plus 1 is 91, so we then go to 2 equals, from up here again, 1 k1 plus r2, and we see that k1 would be 2, because 2 times 1 gives us 2, r2 would be 0, so now we would have 2 times 1, or 2 equals 1 times 2 plus 0, and again, using what we had up here, we would see that the GCF of n, or of 91 and 2 is equal to 1. So again, we want something not equal to 1, so we'd have to retry again by picking a new value of g. So we see that we've shifted the problem from trying to guess a prime factor of n to now trying to guess a common factor, or a number that shares a common factor with n, which is in itself a challenging problem. So what we'll do next is we'll try to show a way to find good guesses, or to find values of g that share a common factor with n. So we've seen that using Euclid's method, we can solve for the greatest common factors between two integer numbers. As it turns out, solving Euclid's method is not computationally taxing on a modern computer. However, the usefulness of Euclid's method relies on having a value g, which is not co-prime to n. Recall that g is some value that we guess between 1 and n. However, unfortunately, in a situation where n is a large semi-prime number, it's far more likely that a random guess of g will be co-prime to n rather than share a common factor. In the case of the value 91, our first guess, we just so happen to pick 26, which shares a common factor of 13 with n. But if we had just taken an iterative approach, starting with 2 wouldn't work, 3 wouldn't work, 4 wouldn't work, 5 wouldn't work, we would have had to go all the way to 7 before finding a guess that actually worked. And for very large n, this approach would take even more time to find a value that shares a common factor with n. So to determine a value of g that does share a common factor of n, such that we can use Euclid's algorithm to find the factors, or the common factors, thereby finding a factor of n, what we'll do is we'll define the expression g to the p equals m times n plus 1. Where here p and m are both integers, so what we're stating here is that by taking a value g, which is co-prime to n, right? Because initially when we make our guess, we can check if g is shares a common factor with n using Euclid's method. If it's not, if it's co-prime to n, then we can multiply it by itself consecutive times until we arrive at a value such that g to the p is equal to some multiple of n plus 1. And you might ask, why are we using this expression of a multiple plus 1? However, we'll see in a minute why this is useful. And just as an aside, another way to express this would be g to the p mod n equal to 1. So we're searching for, we're given n, we pick a random value g that is greater than 1 but less than n, and we search for a value p such that this expression is true. And just recall that this expression of mod n, g to the p mod n, is equivalent to finding the remainder of g to the p over n equal to 1. But so we'll come back to this form in a minute. For now, let's focus on this form, because what we can see is that by rearranging this, by subtracting that 1 over from here, we'll get g to the p minus 1 is equal to some multiple of n. And what we can now do is we can expand this to obtain the form g to the p over 2 minus 1 times g to the p over 2 plus 1 is equal to some multiple of n. And just to double check that this works, g to the p over 2 minus 1 times g to the p over 2 plus 1. Multiplying these together, we'll get g to the p, the 2's cancel, and then we'll have plus g to the p over 2. Then we'll have minus g to the p over 2 minus 1. These values will cancel, and we can see that we're left with the equivalent expression of g to the p minus 1. So these are in fact equivalent. Now, why do we want it in this form? What is the benefit here? Well, you can see we're in the form of a times b equals m times n. And now, in this case, all of these are integers, correct? So in the case where we have a, b, m, and n, all as integer values, then we have that, then we can say that one of these, a or b, must share a common factor with n, right? And we can check this, because if n is a semi-prime number, then it can be expressed as, in the form, n can be expressed as the product of all of its prime factors to some power, right? So in the form of 200, we saw that 2 was multiplied multiple times. That would be this exponent here, or it can just be 0 if there's only 1. So it would be n naught times to the k naught times n1 to k1. This would continue out to some value n, say j, kj. In other words, we can express n as the product of, say, I equals 0 to j of ni to ki, where I is some value greater than 0, or greater than or equal to 0, less than or equal to j. So just I runs over the number of distinct prime factors that multiply together to make n. And in this case, we can re-express this expression here as a times b over n is equal to m. And so now in the case that one of these numbers is not coprime, or is coprime to n, right? So if, let's say, a is coprime to n, then that would mean that a divided by n, or divided by any little n, so any value which is a common factor of n, would not be equal to a integer value, right? Because if a is coprime to n, then they share no factors, so dividing by a factor of n would not yield an integer value. Well, if this is true, but we have that a times b over n is equal to an integer m, right, because m is an integer, then it must be true that b divided by some value, some factor of n, is equal to an integer, right? Because, and this is because if we have two non-integer numbers, right, so if b was also coprime to n, then b divided by ni, any of these ni's, would not be an integer. So if that was true, and both of these were not integer values, then it would be impossible to obtain an integer value of m for a times b over n, unless one of these was an integer, or they're the reciprocal of each other. Where here, reciprocal multiplication can only happen if a or b are not coprime to n, correct? Because for a reciprocal, we would need ni times some b or a over ni times some b over n, say k, equal to integer, would only be true if a is some integer multiple of nk or b is some integer multiple of ni. But if they're both co-prime to n, then that would not be true. So we see that in this form, either a or b must share a common factor with n. So by setting it up in this form and obtaining this form here, we see that we found a case where one of these expressions will share a common factor with n. So at that point, we can then use Euclid's method to find the greatest common factor of g to the p over 2 minus 1 and n, or g to the p over 2 plus 1 with n, in which case we have found a prime factor of n, right? Because one of these will share a factor, we'll get that factor, we can divide n by it, and we'll have the two prime numbers that multiply to the coprime, or to the semi-prime n. This is all well and good, but you can see we still haven't found a way to determine p efficiently. So we found a way to find expressions that will share a common factor with n, but we have not found a way to quickly determine p. In this next part, I will show how we can express this in such a way that the value p will be periodic. And when we get to Shor's algorithm, we'll see that finding this periodic, or solving for this periodic function, will be exponentially faster using quantum algorithms. So recall that we previously stated that our expression g to the p equals m times n plus 1 could be expressed as, or was equivalent to g to the p mod n equal to 1. As it turns out, this expression here will be periodic with p. So for any solution of p which satisfies this, we'll see that p times n for any integer small n will also satisfy this relationship. So explicitly, g to the p mod n equals g to the 2p mod n, which will equal g to the np mod n equals 1. Again, where n is just some integer value. Now, a proof of this was given by Euler. However, rather than work through this proof, I'll simply show an example to illustrate that it's true. So going back to our previous example with n equal to 91 and g equal to 2, which we saw earlier that 2 is coprime to n, we can set up using this formula. So we'll have 2 to the p mod 91, and we want to find where this is equal to 1. And so my claim is that by iterating over integer values for p, we will find a value for p where this is true, and that this value of p, any integer multiple of that, will also be a solution to this equation. So we can check this starting with p equal to 0. So 2 to the 0 mod 91 equals probably 1 mod 91. So 91 divides 1 0 times with a remainder of 1. We can increase p by 1. So well, 2 to the 1 mod 91, which will equal 2 mod 91. 91 divides 2 0 times, so 0 with a remainder of 2. And this will continue until we reach until we reach a value of p equal to 12. So well, 2 to the 12 mod 91, and this is going to be equal to 4096 mod 91, and we'll see that this is indeed equal to 1. So now we found our first value p where this expression holds, and our claim is that for any integer multiple of 12, this same relationship will hold. So we can check this right now that if we have 2 raised to 2 times 12 mod 91, that this will equal 2 to the 24 mod 91, which equals 16777 mod 91, and we can check, and you can check that this is in fact equal to 1. Similarly, we can do the same thing for 2 to the 36 and 2 to the 48, and if you check that, you'll find that the same relationship holds, that we'll have mod 91 equal to 1. So these solutions are indeed periodic, and now we found a way to solve for p, in that we can just find the period. And using what we had earlier, where we saw the GCF of g to the p over 2 plus or minus 1 n, where we stated that at least one of these will give us a common factor with n, we can set this up with our value of p in g. So we have 2 to the 12 over 2 plus or minus 1 and 91, where we'll see that 2 to the 12 over 2 is equal to 64, right, 2 to the 6. So we'll have GCF of 64 plus or minus 1 and 91, which we can then use Euler's algorithm to solve. And if we do that, we'll find that we have, for the GCF of 65 and 91, that we have 13. And we can check this, right? So 13 we know is a factor of 91 from earlier, but 13 times 5 will get us 65, so that's true. And GCF of 64 for the minus, and 91 will get us 7, which we know from earlier again is one of the other prime factors of 91. And we can check for 63, that would be 7 times 9. So we see that we are able to, in fact, find the prime factors. So the one thing of interest here is that we've now changed this into a problem, or we've now converted the problem of solving for p into a problem of finding the period of a function. Right now that might not seem like a large upgrade over what we've been doing, but as we'll see in the next few sections, that Shor's algorithm is able to employ techniques from quantum algorithms to exponentially reduce the computation time needed to solve this type of periodic function.
The efficiency increase from the Shor's algorithm strategy comes specifically from the quantum Fourier transform, or QFT. Quantum Fourier transform in this QFT, and the and quantum phase estimation. So phase estimation, or QPE. Where QFT is similar to the classical Fourier transform. However, rather than operating on classical wave patterns, the QFT operates on a quantum wave function representing the superposition of quantum states. And QPE is a method for finding the eigenvalue of a unitary operator. So we'll see that while this concept may seem unrelated to factorization, we'll show that we can reformulate the problem such that a set of unitary operators' eigenvalues will lead directly to the period that we are searching for. A full description of QFT and QPE will follow.
So begin by talking about the quantum Fourier transform, or QFT. At a high level, the QFT is a change of basis from the computational basis to the Fourier basis. So for a one-qubit system, the computational basis is simply the 0 and 1 states. And our Fourier basis are the plus and minus states. So when we say the QFT is a change of basis from the computational to the Fourier basis, we're stating that we're going from the state to these states. So explicitly for this one qubit system, the QFT of on the 0 state is going to give us the plus state, whereas the QFT on the 1 state will give us the minus state, where for the one qubit system, we can see this quantum Fourier transform is going to be equivalent to the Hadamard gate, because the plus state, remember, is the uniform superposition, so 1 over the square root of 2 of the 0 state and the 1 state, and similarly the minus state is the uniform superposition, again, of the 0 state and the 1 state, only with a phase factor applied. To define the QFT in more general terms, we'll start by looking at classical Fourier analysis. So recall that the classical Fourier transform, or CFT, is a way of decomposing a signal into the sinusoidal waves that form it. So if we have some complex signal like this, the CFT would be a way of taking this and breaking it down into
some combination of sinusoidal waves that add together to form this more complex wave function. Now, for the quantum Fourier transform, rather than dealing with classical wave patterns, what we'll be dealing with are the quantum wave functions, specifically quantum wave functions representing the superposition of quantum states. In a quantum circuit, these superpositions of states will be continuous. However, the states themselves will be discrete, and therefore we start with the classical Fourier series. The classical Fourier series is given by, it's denoted by, for a function f of x, this f of x with a tilde over it. So this is the CFT on our function f of x, and this is given by the expression, given by a summation from n equals minus infinity to infinity of an e to the I 2 pi n over p on x, where here the an represents the amplitude of a given sinusoidal and p represents the period. Therefore, this n over p represents the frequency. So now, reinterpreting this into the QFT, we take this amplitude an to be the uniform quantum amplitude 1 over square root of n, where this n now represents the total number of unique states for n number of qubits. So n is going to equal 2 to the n, where this n is the number of qubits in a quantum circuit, where, again, because n represents the total number of states, because big N represents the total number of states, if there are n qubits, each of which could be in the state 0 or 1, the total number of states will be represented by 2 to the n. Similarly, for our frequency, n over p, this will now be represented by y over n. And we'll see that this will control the phase applied to each basis state. So for the QFT, writing this out in terms of a formula, we have, again, our x state now, rather than our function, again with the tilde to denote that this is in the Fourier basis, equal to the quantum Fourier transform on x, which equals, again, we can pull this, or now we can pull this amplitude out because it no longer depends on small n, because it's going to be a uniform, over y equals 0 and minus 1, and we'll be summing e to the I 2 pi over n, x times y, applied on the state y. So, looking at this expression and what we have from before, we can check that this quantum Fourier transform indeed does take us from the computational base to the Fourier basis, at least for the 1 qubit system we can check. So, looking at this, for the 1 qubit system, we'll have n equals to 2 to the 1, because it's 1 qubit, which equals 2. Therefore, we can say for x equal to 0, so if we start in this state, we'll have QFT of 0 equal to 1 over square root of 2 here. And now our summation, so for y equals 0, we will have e to the I 2 pi over n, which is 2, so these will cancel. Our x here is going to be 0, so 0 times our y here, in the first part of the summation will be 0, times 0 on our 0 state, and we will add that to, again, e to the I 2 pi over 2 from here. These cancel again. Now we'll have, again, x equal to 0, y equal to 1, so we apply to the 1 state. And we see here that because both of these are going to be 0, we'll have e to the 0 and e to the 0 here. Therefore, e to the 0 equals 1. So QFT on 0 will equal 1 over square root of 2 plus 0 state plus our 1 state, which is indeed equal to the plus state, as we expected from what we saw earlier. Now we can do the same thing for our 1 state. So we'll have QFT operating on 1. And now we again have n equal to 2. So we'll again have here our 1 over square root of 2 And now for our summation, for y equals to 0, we'll have e to the I, again, 2 pi over 2, cancel the 2's. And now we'll have our 1 state for x times 0 for y. This is the first part of the summation. Again, on the 0 state, plus our e to the I 2 pi over 2, 2's cancel, our 1 state from here, now multiplied by our 1 state for the next part of the summation on y, on our 1 state. And so now what we'll see is that here we have 1 times 0, so this will again be 0, and e to the 0 is 1. However, here we'll have e to the I pi times 1. So e to the I pi is not 0, it's negative 1. So writing this out, we'll see we have QFT on 1 equal to 1 over square root of 2 on our 0 state, now minus from this e to the I pi, our 1 state, which is in fact the minus state. So we see here that our results from using this formula for the quantum Fourier transform are indeed in line with what we'd expect. So we've kind of motivated this expression for the quantum Fourier transform. However, it would be good to show how this can be used more generally in quantum circuits. Right? So in quantum circuits, these states y are going to be represented by qubits. So for example, if we have the state y equal to 5, what this is really telling us is that we have a 3-qubit system of 1, 0, 1. Right? Because in binary, this would be 1 times 2 to the 2 plus 0 times 2 to the 1 plus 1 times 2 to the 0, which this is 4 plus 0 plus 1 equals the 5 that we're looking for here. So having said that, in general, these states y that appear here can be represented as the expansion, or as their expanded version, y1, y2, dot, 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 all the way to yn, which, as we see here, can be represented by the summation over some value k, or some integer k, from 1 to n, where n, again, being the number of qubits. And here we'll have yk 2 to the n minus k, which, again, will work out like this. So, therefore, we can revisit our expression here for QFT, operating on x, and say we have x equal to 1 over the square root of n still, and now we have our sum, n minus 1, y equals 0, to n minus 1, of, now what we'll have is e to the I 2 pi, again, over n, which recall that n equals 2 to the n, so n equals 2 to the n, and now instead of just having our, well, I guess we can put our x, but now instead of just having our y, what we'll have is we'll have this summation over y to the k to n minus k, again from k equals 1 to n, and all this on our state y1 to yn from here, which we could expand out. So now canceling this 2 to the n with the n here, we'll have a 2 to the minus k, so we see that we can write this as 1 over square root of n, again our summation from y equals 0 to into the minus 1, e to the I 2 pi x, and now we'll have our summation yk over 2k, and we will have, again, our states y1 to yn. So looking at this and noting that we have a summation in the exponential, we can see that this could be expressed instead as a product over k, rather than the summation over k. Because if you recall, e to the a plus b is equivalent to ea times eb. Alright, so our summation could be expressed as this product. So re-expressing this in terms of our product, we'll have 1 over square root of n minus 1, again still our summation over y equals 0,
but now we'll have a product over k equals 1 to n, and we'll have our e to the 2 pi I x yk, all of this over our 2k, 2 to the k, from this to the minus k, and all that on our y state, our y basis states. And now, note that because k is a vector index, right, because y is going to be a vector like this, the products will in fact be tensor products. So keeping that in mind, now looking at our sum over y, this is actually over the 2 to the n states, right, from 0 to n minus 1. So this summation can be expanded into a sum over each qubit, right? So our summation over y from y equals 0 to n minus 1 can be expanded into the individual qubits. So y1 from here equal to 0, 1, y2 equal to 0 to 1, representing the 0, 1 states, all the way out to our yn equals 0 to 1. So using that this product will be tensor products due to the index k being the index of a vector, and using that the summation can be expanded into the individual qubits, we find that we can express this as 1 over the square root of n multiplied by all the states, expanded into 0 plus e to the 2 pi ix over 2 in the one state, tensor product, again for the first qubit, tensor product, or for the two states here, represented here. Now we have our tensor product for the second. This will be e to the 0 plus e to the 2 pi I 2 to the 2 x 1, where we see this 2 to the 2 coming from this 2 to the k. So initially it's 1, next it's 2 for k to n, and this tensor product will continue until we reach our final expression plus the 0 state with this phase factor 2 to the pi I over 2 to the n x on 1. Again, where this 2 to the n is coming from us running over these possibilities. And now each term is the state of the n qubits after applying the quantum Fourier transform. So note that an important thing to notice is that these x terms here are representing the full state x over all n qubits. And an important distinction to notice that because the QFT is operating on quantum states, it must be unitary. That is that QFT minus 1 on QFT on x will just return us to x. And this will come in handy later when we discuss the quantum phase estimate. Where note that we've now in essence applied a way, or found a way to apply a quantum kickback. So if we could somehow encode in this state some information about the period, you see here we can kick it back. Likewise, if we, by this property, if we can find a state, or if we can arrive at a state in this form, we can apply the inverse quantum Fourier transform to recover a state in the computational basis, such that we can measure it and get meaningful information out of it. As its name may suggest, the quantum phase estimation, or QPE, is a method to estimate the phase applied to a quantum system. More specifically, the QPE is used to estimate the phase corresponding to an eigenvalue of a unitary operator. So recall that for a unitary operator U, the modulus squared of its eigenvalues will be 1. So in other words, the eigenvalues of a unitary operator can be appropriately represented by e to the I 2 pi phi, right? Because recall that this squared will simply give us e to the 0, because the plus and minus I, which equals 1. So we can see this eigenvalue for a unitary operator is ideal, as it obeys the fact that we need a unit modulus.
Therefore, for an eigenstate, or for a unitary operator u with eigenstate phi, we can say that this will have eigenvalue e to the I 2 pi phi on psi. So applying the unitary operator to its eigenstate, we get the eigenvalue out and remain in the eigenstate. So in practice, the QP utilizes the Hadamard gate and controlled U gates to apply a quantum kickback on a set of qubits, producing a similar state to what we saw previously, where we had the expanded state of tensor products for each qubit. So what we can do is we can apply this unitary operator to an eigenstate. We can use quantum kickback to encode this state into our system, and then we can apply the inverse quantum Fourier transform, or the QFT dagger, to encode this information on the state itself, such that it'll be measurable. And next we'll show an example of how this works. So to show an example of QP in action, let's first begin with two sets of qubit registers. So register 1 will contain a set of n qubits initialized to 0. So we can call this circuit R. Describe the circuit as S0, and we'll have n qubits in our 0 state. And then in our second register, we'll have qubits that form the eigenstate of U that we saw previously as psi, right, where psi is an eigenstate of U. So as a first step, what we'll do is apply the Hamiltonian on the n qubits, to each of the n qubits in the first register, so the qubits in the 0 state, to obtain n qubits in the plus state. So what we'll have is applying the Hadamard on here to the end. We will have S1 equal to 1 over the square root of 2 to the n for each of the terms on each of these 0 states. And we'll have again the plus state from the Hadamard over the n qubits and our eigenstate of U. So next what we can do is we can apply a controlled U gate on the qubits in psi to apply a phase kickback onto the one state portion of the superposition. Note that the control is encoded in U as K, UK, psi. Therefore, each qubit will receive a portion U to 2, say J, Kj, from each of the n qubit Ks, where our K here is these states. So our K is equal to our plus state, which is the state, and there's n of them. Where here J is simply an index from 0 to the summing over 0 to the total number of qubits n. So put that here. J is going from 0 to the number of qubits n minus 1, because we're starting at 0. So using this for Kj equal to 0, we have U0, which equals I, just our identity matrix. But for Kj equal to 1, so for our one portion of the state, we'll have that U will have U to 2j times 1, because Kj is now 1, which just equals U to 2j. So now applying this on psi, we find that U to 2j on psi is equivalent to U to 2j minus 1 on U, so just pulling this U out on psi, which is equivalent to U to 2j minus 1 e to the I 2 pi phi on psi, which we can continue and get U to the 2j
minus 2, so pulling out another u, e to the I 2 pi phi u on psi. This will act again, pulling up another factor of e to the I 2 pi, and so continuing to do this many times, we'll find is we'll eventually arrive in the state e to the I 2 pi phi 2 to the j 1 psi. And so, as we saw here, from here, this phase will be kicked back onto our one state, and therefore we will obtain an expression of S2 equals 1 to the d square root of n, where again n here is equal to 2 to the n, the total number of states, because we're in an equal superposition. And we'll have over each of our qubits in the first register, which are in this plus state, e to the I 2 pi phi 2 to the j. And we'll have n of these. So for each of these, we'll have a different value of j running from 0 to n minus 1. And we can express this more completely as a summation over n or over k on our k states. Again, these are our plus states. Tensor product with psi. So similar to what we said here, we'll have a sum over all of these tensor product with psi. So what we'll find is an expression similar to or equal to our 0 state plus e to the I 2 pi phi 2 to the it's from this 2 to the j, 2 to the n minus 1, our one state, tensor product with 0 plus e to the I 2 pi phi 2 to the n minus 2 on our one state. And this tensor product will continue until we reach the final expression, 0 plus e to the I 2 pi phi 2 to the 0 on 1. And all of this acting on our product with phi. And note that this expression is in a very similar form to what we found previously doing our quantum Fourier transform, where we ended up with this expression. And so you can see the only major difference here is that this x value doesn't appear. Instead, here, x is replaced with 2 to the n, so x is equivalent to 2 to the n phi here. So we can see that this is in our quantum Fourier, or in the same format as our original, what we originally attained with applying our quantum Fourier transform. And note that the QFT is a unitary operator. Therefore, we can simply apply the inverse quantum Fourier transform to this state to extract this information from this Fourier basis into our computational basis. So to encode the phase phi onto our measurable states, we can again apply that inverse quantum Fourier transform on our state S2, and this will give us something approximately equal to 2 to the n phi. Note that this applying this quantum Fourier transform, or the inverse of the quantum Fourier transform, will not guarantee that we measure this state. However, this will be the most probable state to measure. So therefore, we see that QPE allows us to uncover information about the phases that we apply on our n qubits in register 1 that were applied using our unitary operator. So what we need now is to find a unitary operator such that the phase we're encoding carries information about the period of our of our equation from earlier, which will give us the period we need to find the common factors of n. So we've seen how using QPE and applying the inverse quantum Fourier transform on that state, we can extract information about the phase into the measurable state. But it's not clear how doing this will actually help us solve for the period that we're looking for. So Shor's algorithm solution is to make this phase information particularly useful to the factorization by defining u in the following way. So if we have u on y, that gives gy mod n, then we can work out the eigenstate here. So let's first say that we are in we begin with the state y equal to 1. So say y is equal to 1, and we apply u. So we have u1 is going to equal g1 mod n. Now if we repeatedly apply u, so say we apply u again, we'll have u squared equal to u on 1, which equals ug mod n from here. And now we'll see that this it gives us g times g mod n mod n. So we'll see here that we note now that we saw earlier this function will be periodic in nature. So therefore, after applying u p number of times, we would expect to recover our initial state 1, correct? Because this is a periodic function. So that is up should up acting on 1 should return the state 1. So now it can be shown that for u, given defined as we did up here, the possible eigenvalues in eigenstates can be defined as eigenstate us defined as 1 over the square root of p summation over k equals 0 to p minus 1 e to the minus I 2 pi sk over p on our state gk mod n. And this will have eigenvalue, or this will have an eigenvalue of e to the 2 pi is over p. So we can see that with this eigenvalue, in these forms, we have superposition of the states for each k iteration from 0 to our period minus 1. And here s is any integer in this range. So we now have unique eigenstate for each integer value s from 0 to p minus 1. And if we sum up all of these eigenstates, the different phases will cancel out all the computational basis states except for 1. What we can see by looking at this form here and looking at what we had seen earlier, where we saw that our general form for u acting on an eigenstate is e to the I 2 pi phi on psi. So this is our general form of an eigenstate. Comparing these two, we can see that here phi is simply going to be s over p. So by defining u in the following way, we find that its eigenvalue will be equivalent to, we'll have phi equal to s over p, where p here is this period we're looking for. So from what we found earlier, where we could, from what we found up here, where we can use the quantum Fourier or quantum phase estimation to arrive in the state S2 and apply the inverse quantum Fourier transform to S2 to extract the phase information. If our phase is now S over P, then we see that we can extract information about our period into our state, information that is measurable in our quantum circuit. So that is the magic behind Shor's algorithm, is that to estimate this phase P, we can use the quantum Fourier transform, or we can use the quantum phase estimation and the inverse quantum Fourier transform to extract the period information into a measurable. So we have finally reached a step where we can put everything all together and define Shor's factoring algorithm. So as we'll see, this will have classical parts, some of the classical parts that we described earlier, as well as the quantum parts that we just went over. So to factor a large semi-prime number n, we begin by picking a random number g, our guess, that is between 1 and n. So when we make our guess, we check to see that if it itself is a factor of n by searching for the greatest common factor of g and n using Euclid's method. We define this as k. So if k is not equal to 1, then we found a non-trivial common factor between the two. Because we found a factor, we can simply find n over k. K will be our factor, and we're done. We have both our factors, k and n over k. However, as we mentioned earlier, it's far more likely, especially for a large semi-prime number, that k, or that g and n will be coprime, so that k equals 1. In this case, we move on to trying to find the smallest p-value such that g to the p mod n equals 1. Again, we saw that this will be periodic, and we went through all the steps of showing how, because this is periodic, we can use the quantum phase estimation to encode this information in a phase on a quantum state, and then use the inverse quantum Fourier transform to bring this phase information containing information about p into a measurable state, and then we can then extract p. And finally, with p found, we can compute the greatest common factor between n and g to the p over 2 plus or minus 1, as we saw earlier. This will guarantee that we find that one of these will give us a common factor of n. And again, with our common factor found of n, we can compute n over the common factor to find the other prime factor, and we have found our prime factors of n. I should say that all of these steps are given in much more detail in my paper. Additionally, an example of going through the actual quantum circuit that encodes all of these steps is given in that paper. So be sure to read that for more information. One final thing to note is that in order to factor very large semi-prime numbers, it requires a large number of qubits. So for a larger n, it will require more qubits to sufficiently encode to sufficiently carry out the quantum phase estimation to encode the information about p, and likewise to carry out the quantum Fourier transform, or the inverse of the quantum Fourier transform. So in modern days, right now, we currently don't have large enough quantum computers that are sufficiently error tolerant to carry out Shor's algorithm for very large semi-prime numbers. So at current times, the RSA encryption method and encryption methods like it that rely on the secrecy of the prime factors of very large semi-prime numbers are still sufficient. However, as technology advances and quantum computers become more powerful and become larger, Shor's algorithm will become a reality. And at that time, the effectiveness of much of our modern encryption modern encryption techniques will become obsolete. So this obviously poses a massive threat to both personal privacy, as well as a grave danger to national security, and therefore global stability. So for these reasons, understanding the implementation of Shor's algorithm and developing quantum-proof encryption methods before Shor's algorithm is able to operate on large quantum computers will be of the utmost importance. The future of Shor's algorithm will undoubtedly be among the most impactful developments in modern history. I hope that this was a good lesson on Shor's algorithm and gave you a good amount of information. Again, I have a paper that goes along with this presentation that I would encourage you to read for more information or for more clarity on anything in this talk that wasn't clear. That concludes my presentation on Shor's factoring algorithm. Thank you very much for a great semester and for a great year.